Greetings and welcome, friends. Today we are talking about conditional statements. Conditional statements in which the second half of the statement is only applied if the first half is satisfactorily true. So a conditional statement is a logical statement that has two parts, a hypothesis, P, and a conclusion, Q. So we'll use this kind of if P then Q notation kind of to summarize these things so we can minimize the amount of writing we might do. Or we can kind of have a notation to describe these components. You can also have this P and then arrow is kind of implies is what that means. The arrow implies the word implies, actually. I just realized is kind of like a crazy idea there. But so these conditional statements can be written in if-then form. So the if part contains the hypothesis, the then part contains the conclusion. So, let's look at example 1. Use red to identify the hypothesis and blue to identify the conclusion. You guys might not have those colors, so you might have to choose to rearrange. So, all birds have feathers means that if an animal is a bird, then feathers. Hooray! Right? So, let's write that statement. So, if... And it takes a little while getting used to this. If an animal is a bird, I guess I could even say if an object is a bird. If thing bird, right? If bird, then it has feathers. I'm assuming a turkey you buy for Thanksgiving is no longer a bird. It's a bird carcass. I don't know. It's food at that point. I don't know. But now as far as I could write a conditional statement, but my conditional statement could be false. So you could have just thought of maybe we could consider that a valid counterexample, disproving the truthiness of my statement. Let's see. If you are in Texas, careful. Pivotal word right here. You are in Texas if you are in Houston. So notice this actually was a kind of rearranged. The hypothesis actually showed up at the end, and the conclusion was written at the beginning. So if I want to write this in if-then form, I would say, if you are in Houston, then you are in Texas, right? Why can't we just get back to the math where we're not writing sentences, you know? Okay, so that would be a counterexample. Is there another city or town named Houston? Is there a country named Houston? Okay, so counterexample, CE, you're claiming Scotland, maybe? If that's how you spell Scotland, I don't even know. Sure, counterexample. I don't know. I'm Irish and Finnish, and not a great speller apparently. So I don't even know actually. Is that a bad thing? Should I know more about my heritage? Actually, I don't know if you're asking, but is this related to the projects on display in the Social Studies hallway here at Brattleboro Union High School? Okay, well, there's some wonderful projects about Ireland in the hallway right now. Yeah. So let's see. A negation of a statement is the opposite of the original statement. To write negation of statement P, you can use this little squiggly tilde, I believe is the name of that symbol, before the letter. So not P is written as nah, P, nah. Nah, right? And so, guys, this is going to be the most difficult questions you've ever had. Example 2. Please get this right. All right, write the negation of the statement, the ball is red. The ball is not red. All right. Excellent. Excellent. Guys, I think we're going to pass this course. All right, now this one's slightly trickier. What is the negation of the statement the cat is not black? The cat is not black, double negative, or the cat is black, right? Oh, right. I mean, at this point, you guys are like, so like, this is weird, the weirdest stuff. I have no idea. Sure, that could have easily been a technical thing of you need to write not. You're right. Anything is believable right now as far as the potential absurdity of what I'm showing you. Potential. Although, logic is perhaps arguably the least absurd thing in our universe. So in terms of types of statements, I can actually rearrange statements and have interesting results. I can rearrange these kind of if-then statements. Let's see, can I line it up? It's got a gap already. That's fine. And it's offset. Guys, I'm not perfect. It's okay. All right? It's all right. All right. So if I have a conditional statement in if P then Q form, the symbols would be P implies Q. This idea of a converse is when you exchange the hypothesis and conclusion. We've already talked about that in some of our explorations earlier, where a conditional statement was true, but its converse was false, right? Like if a figure is a square, then it is a rectangle, was true, but the converse, if a figure is a rectangle, then it is a square, was not true. All right, because we could think of the counterexample. So this is a converse, if Q, then P. The inverse keeps the same order, but negates the two statements. All right, so yeah, so not P implies not Q, right? Or if not P, then not Q. And so these are a little bit weird. And then contrapositive does both of those things at the same time. It flips it and negates it. It's not P implies not Q. Now, interesting result of this, right? I know, like, you guys are just like, what? Like, this is weird. A conditional statement and its contrapositive are either both true or both false. Similarly, the converse and inverse of a conditional statement are either both true or both false. Wow. And then if two statements are both true or both false, they are called equivalent statements. They come out with the same logical conclusion. So if I know a conditional statement, let's say if square, then rectangle. Let's say that's that. That's then saying I immediately will know that its contrapositive is true, which would be if not rectangle, not square. Does that seem feasible? Right, so if the original conditional statement is true, then its contrapositive will also be true. And it turns out logically linked as well are converses and inverses. All right, so that's kind of a interesting result. So like the moment you recognize a statement is true, you can then actually find a paired up statement that might be obvious, but it is also going to result in truth. And then I think I've got a common error, a little warning, that those things are paired in truth. Let's see, can I paste this right here? Ooh, common error. Just because a conditional statement and its contrapositive are both true, actually, I just realized we could really like step up the meta here, and I could like make this itself an if-then statement. That's crazy. But yeah, if conditional statement and contrapositive are true, does not mean that the others are false. Everything can be true sometimes. Okay, so yeah, that's interesting thing to be aware of. Okay, here we go. Let's do example 3. Oh man, I don't like writing as much as I like typing, to be honest. When it comes to words, I guess with math, sometimes the typing math symbols can be challenging because our keyboards don't have all the symbols on them. Let's see, let P be you are a guitar player, and let Q be you are a musician. Now, we're not here to troll guitar players or musicians, so we're not here to like we're not gonna, have some sick burn here that we're trying to do. Like, we're just gonna assume, all right, here we go. You guys know what I'm talking about. Here we go. So it says first, let's write the conditional statement. So if, we'll simplify this for sake of time. So if guitar player, guitar, tocar la guitarra, then musician. All right. Now let me ask you this. Does that seem true to you or false? True. All right. Once again, no sick burns on guitar players. And I mean, in reality, we'd be applying it to drummers if we were going to have a... Oh, I'm just kidding. I don't want to have some hate in the comments. We're cool. All right, let's see. The converse would be if... Perfect. If musician, right? So we're getting this, even though it's kind of like cumbersome. Then guitar player. How do you feel about the truth of that? Sometimes true. And because it's sometimes false, that means this is a false logic. This is a statement that you could not rely on consistently, right? Because there's a single counterexample. And what would an example be of a counterexample? All right, saxophone player. I was thinking more of like when SpongeBob was in the marching band and like there's the didgeridoo player, but saxophone also is sufficient as an answer. There are musicians who are not guitar players, so that's a counterexample. All right, inverse. Can someone help me with the inverse here? So if not guitar, then not musician. And perhaps now that we have an example here, you might see how the converse and inverse are linked. Then not musician. And so true or false? I've already selected red. It's false because these two are linked. And yeah, it will, right? The last one is going to be true. But let me ask this question. What's a counterexample of this statement C first? Right. So I could think of a person who is not a guitar player in which this conclusion would be false, right? And that would once again be the cellist, the guitar player, right? The acapellist. I don't know. And let's see if we can do this last one. If not Q, then not P. So this would be if not musician. Then not guitar player. Right, so I mean, now that we're actually like thinking about an actual example here, right, we can kind of see, oh, okay, all right, there we go. That makes sense, right? So if someone's not a musician, then they can't be like, oh, but I dabble in the guitar. I've been playing it for a decade, and yeah, I sometimes tour around the world and do some awesome like solos, right? You're like, nah, you're still a musician. All right, there you go. Right. So there's example 3. Also, in case you can't visualize this, tell you what, here's a picture. Oh, okay. Oh, now I understand. I didn't know what a guitar was. All right, now I know. Right. Just in case you guys were worried. Let's see. Using definitions. So I foreshadowed this earlier. So fortunately, you're welcome that you guys don't have to write this down, right? You can write a definition as a conditional statement in if-then form or as its converse. So definitions are flip-flopped. Both the conditional statement and its converse are true when pulling from a definition. So if-then and converse, both true, etc. For example, consider the definition of perpendicular lines. If two lines form a right angle, they are perpendicular lines. So there's a new definition for us, a definition that we will be able to use in our proofs in the future. It says you can also write the definition using the converse. If two lines are perpendicular lines, then they intersect to form a right angle. All right, so you can write line L is perpendicular to line M as line L is perpendicular. Oh, no, sorry. I was thinking they were doing the logical thing. They're just teaching us a new symbol. This symbol means perpendicular. My bad. I was like emphasizing the wrong syllables there. So yeah, perpendicular is denoted by that symbol. Side note, what's a symbol for parallel? Do you guys know? All right, I'm getting some awesome hand gestures. It's good. You guys are all referees calling a field goal. It's kind of like they're taller than yeah, they're longer than an equal sign, but it's basically like two absolute value things, right? Except they're side by side. It's literally like a picture of two parallel segments there. So perpendicular is an upside down T. Parallel symbol is denoted by that. Another way we can write. Actually, oh, never mind. I was gonna jump the gun. I don't want to jump the gun. All right, here we go. Aha! Welcome back. Welcome back. Oh man, you've been missing out on some great logic here. Let's see. Decide whether each statement about the diagram is true. Explain your answer using definitions you have learned. All right. Someone tell me, what does first of all this mean? What is that even saying? Perpendicular to line BD. So AC and BD. Do you guys feel that's true or false? Green or red? True. And we would say by def of, right? Def of perp, right? Because they form a right angle, therefore they are perpendicular. All right, how about angle AEB and CEB? So that's this angle and this angle here. Are they a linear pair? True. By def of linear pair, they share a common side. They have non-overlapping interiors, and their non-common sides are forming opposite rays. So by def of LP. All right. Nice, nice. Yeah, and like I said, mathematicians are efficiently lazy people. That's a phrase I commonly say. And like literally, mathematicians, we were the first ones to come up with like texting shorthand before texting through cell phones was a thing. Right? We come up with crazy symbols so I don't have to write whole words. Yeah, represent math people. All right, let's see. EA and EB are opposite rays. How do we feel? Falseness. EA, it's in the game, and EB, those are non-opposite rays. That's false, and it's false because it does not satisfy the definition of opposite rays by def of op rays. Right? Okay. Keep cruising, Mr. Waddy. Come on. All right. So just like I said, definitions can be written as their regular conditional statement form or their converse. We call such a situation biconditional. It's true whichever way it is written. And notice I like this symbol. It's just like, psh, hey, P implies Q, Q implies P. Wherever you start, you can conclude the t'other, right? And what's weird about these is that we might have the phrase show up if and only if between those things. All right, if and only if logic, the idea is that it can kind of be written either way. Let's see if I can get an if and only if statement written for us. Example 5, and then we got to hit truth tables. Come on, Waddy, we can make it. We can make it. All right. So, writing a biconditional statement. All right. So if two lines intersect to form a right angle, then they are perpendicular lines. They're claiming biconditionality here. And so the way I could write this is two lines intersect to form a right angle. And notice I didn't start with the word if. Angle, come on, spell the word angle. And then I'm going to use the phrase if and only if. Okay? If and only if they are perpendicular lines. I love the minimal coefficient of friction on my writing tablet. Not the friction of graphite or paper and ballpoint pen. It's just so glidey. Not that my handwriting is gorgeous or anything, but I live with it. So that's the idea of, oh dear, what's going on here? How did I get, oh, whew. All right, my mouse was stuck as an eyedropper for a minute there. All right, All right. Yeah. Meh. Meh. All right. Truth tables. Yeah, that's where we're going to go. No, this isn't some like middle school challenge. This isn't the game that you see on like the Tonight Show of truth, truth, lie. Here's a truth table. I said that as if like I'm going to drop the mic after this, or like, here's a truth table for you, and then like I'm going to walk away, like just proving my point. But here, in a more friendly tone, is a truth table. So consider for two statements, hypotheses and conclusion, here there are four possible ways that those statements can relate. I could have both of them being true. I could have the first one being true, the second one false. I could have false true or false false, right? So those are four ways that I could have two statements and their truthness. And then I could analyze, well, what about P implies Q? Is this conditional statement true in a situation where true, true is the result? Okay? And so if P is true, which it is, then Q is true, which it is. So this conditional statement is true whenever both of those are true. All right? I'm going to keep going here. It takes a little while to get used to. If P is true and Q is false, that means, okay, and now this is saying, if P is true, which it is, this is arguing that Q will also be true, right? That's the logic here. If P true, then Q true, but Q is not true, and therefore the conditional statement is false. That's the situation in which an if-then statement is wrong, right? So that's why this would be false in that scenario. I don't know how well I'm explaining this. I'm really unsure of myself. I hope it's starting to make sense. So I'm just going to keep going. All right. Now, the conditional statement never gets processed. The if-then logic never applies anytime P is not true. And because of that, I don't care whether Q is true or false. If P is false, I'm not using my logic. I'm not using the statement. So this statement is perfectly valid anytime P is false, because the if-then didn't apply. All right, so that's a truth table. Let's see if we can do example 6 and call it a lesson. Yeah, there's just so much like terminology today. And now I've got my sniffles going, and oh man, no one likes that. It's actually I have heard conclusively from a movie that no one likes a Mr. Sniffles. Conclusive. Then no one likes you. Oh man, yeah. If you have the sniffles, no one like. Oh man, I'm sorry. I wonder if anyone has the last name Sniffles and is a sir that would be referred to as, excuse me, Mr. Sniffles. Right? That'd be pretty good. Maybe I'll change my name someday. So here we go. I've given you guys these tables to fill in. Let's consider the Q implies. Tell you what, internet friends, I'm gonna forget you, internet friends. I'm gonna just leave this here for you now. You guys can figure this out on your own. I'll talk to you later. Bye-bye.